Okay, I had to stop and continue again anyway. So we have just shown that the transfer matrix is necessarily symmetrical if the coordinates that it connects between input and output are self-referencing. That is, are the same coordinates. Coordinates of input and output are collocated. In general, not just for that case, right? In general, the transfer matrix looks like this when we look at it in model coordinates, but for self-referencing is symmetric. So now what I want to show, which is very easy illustrated, right? The denominator on this formula is a scalar. So that does not change whether this is symmetric or not. Now, this is a summation from I1 to n. And what the transfer matrix being symmetric shows is that that summation is symmetric. But what I want to show right now is that that sum is not only symmetric, but that each term in the sum must be symmetric, right? And we show that each sum in the term must be symmetric by simply considering what happens if S, for those not familiar with the Laplace transform, this might, I'm sure it's confusing, but just remember S is a scalar, it's a complex scalar that can be taken as any value, more or less, there are some limits, but can be taken at any value, and when that value is selected, we have the transfer matrix at that S, right? So I can take S to be anything I want, and this transfer matrix must be symmetric at any S. Therefore, let's say that I take S to be infinitely close, or very close as you would like, to lambda I. Then that means that if you sum these terms from I to n, only the ith term would matter. And if only the ith term matter because this denominator is so small, then that means that the numerator must be symmetric for that value of S by itself, right? Indicating that not only the sum is symmetric, but every term is symmetric. At the risk of being unnecessarily explicit, let's just illustrate like this. Let's say that lambda 1 was 1, lambda 2 was 3, and lambda 3 was 5. Just to make an example, right? And then let's say that I choose S equals to 2.99. Okay? Then in that case, if I look at that sum, let's say there were only 3, right? The sum would look like this. Whatever divided by, the numerator divided by S, which is 299 minus 1, that would be 199, right? Times lambda 1 to the p, whatever it is. So we have that. Plus the second term, something, I don't care, divided by 299 minus 3, right? So it would be 0.01, negative, I guess, the way I did it. You know what? I make errors all the time. Let me just minimize my error likelihood by just saying, instead of 299, let me say 3.001. That way I can subtract easier. So for the first term, I have whatever divided by S minus this, that would be 2.001, right? Times lambda 1 to the p. Plus the second term, which is whatever, and then I have 3.001 minus 3 is 0.001 times lambda 3 to the p. Whatever p will depend on the type of measurement, right? Plus whatever in the numerator divided by 3 minus 5, that would be 2, so this is 1.999 or something like that, right? Times 5 to the p. So you can see that this term here is large, right? because I'm dividing by 0.001, so that's 1000, and if this term is large compared to this 2, it dominates, right? Now if 3.001 was not enough, you can also just go like this, right? And that's even closer, and this term would be then so much more large, right? So much larger. The point is that when I evaluate S very close to an eigenvalue, the term that corresponds to the number of the eigenvalues selected dominates the sum. And because the transfer matrix has to be symmetric all the time, then that means that the numerator had to be symmetric independently for each one of the terms. Okay? So that's the demonstration that I use. So we now accept that these terms are themselves symmetric when we have self-referencing. Now, the next thing is, if this is symmetric when it's self-referencing, then it turns out that this second vector tau actually must be proportional to the first one, otherwise the product would not be symmetric. In fact, to show it again, imagine that phi was ABC. If tau is also A times alpha, B times alpha, and C times alpha, that is, if this vector is proportional to this vector, then we will get here A squared alpha, AB alpha, AC alpha, AB alpha, B squared alpha, BC alpha, CA alpha, CB alpha, and C squared alpha, right? And you can see that that matrix is in fact symmetric, right? So the matrix is symmetric, but if this vector here was not proportional to this one, the matrix would not be symmetric. So we conclude that if we have self-referencing, which requires symmetry, then we also have, and we approach our final result, we also have that the vector tau, using notation from MATLAB, or actually I could say, yeah, the vector tau I, comma, like this, right? That would be a row, if you'd like, right? So I could say transposing, so it becomes a column. Multiply times alpha I is actually equal to the vector phi I. Okay? So this, which is a row, if I write it as a column and multiply times a number, it has to be equal to this if I am going to satisfy that this numerator is a symmetric matrix. Okay? Therefore, I can write that the transfer matrix as a function of S, provided that we have self-referencing conditions, is equal to phi, the ith column, multiply times the phi, the ith column again, transpose, that's the tau, multiply times alpha I, divided by S minus lambda I times lambda I to the p. Okay? So my numerator there now is forced to be symmetric, or shows that it's symmetric, right? Okay, so now that we have this situation, we want to say, well, what if I only had one measurement? What if I only had one measurement? What if we only had one measurement? Then if we only had one measurement, we could say that this equation here, a transfer matrix in general, right? Because this was not just for self-reference, this is the general expression, right? It's just that if it's self-referencing, that was symmetric. And so this is the one that's self-referencing, right? This is in general. So if we only had one measurement, we have to use this one because we obviously don't have self-referencing. So we'd have phi, the ith column, multiplied times, this would just be a scalar because there wouldn't be any more rows. And so this would be like this. This can be, in order not to, or to try to keep clarity as much as possible, remember that the definition for tau is equal to phi to the minus 1 times b, where these are the eigenvectors of the A matrix, right? So for a single measurement, for a single input, tau is equal to just one column, right? Because B is one column, you just only have one input. And so the first entry is tau 1, the second entry is tau 2, the second entry is tau 3, and so on. This is for mode 1, this is for mode 2, and so on, right? So again, emphasizing, if we only had one measurement, our transfer matrix would take this form. All I've done is replace this, which used to be a row, by just a number. I'm sorry. Right? Summation remains. So the summation from I1 to N, and we have this. Where this number tau, or this thing that used to be a row vector, becomes one column like this, and for each term of the series is just being picked up one at a time, right? Okay, so let's see if we have this expression evaluated. Consider, for specificity, for simplicity, consider, I don't know, I equals to 2, and say we had 3 measurements. Okay, so let's say there are 3 measurements, and I want to evaluate this thing, and I am looking at the I equal to 2. So for I equal to 2, I would say that in my summation I would have phi. Now let's say that this phi 2 is just A, B, C, right? I measured 3 things. And then I would multiply it times tau 2, because I'm saying I equal to 2, right? So I would make that, and therefore we would find that the contribution of the I equal to 2 term to the transfer matrix would be, what is it? Why do I draw it like a full vector? Where's the eraser? Oh, excuse me. Oh, here. Okay. So this numerator would simply be like this, right? It would just be A tau 2, B tau 2, C tau 2 divided by S minus lambda 2 times lambda 2 to the P, right? I'm trying to simplify by looking at only one term of the series in a specific case where there were 3 measurements. So with 3 measurements, and I'm saying that the phi vector was A, B, C, 3 measurements. Since I only have one input, okay, one input, then we are in this instance where B is one column and tau is now tau 1, tau 2, tau 3, right? So I'm looking at I equal to 2, so we take the A2, and so this product here is just the vector ABC multiplied times tau 2. It looks like this. The denominator is like that. That's not the full transfer matrix, right? That's just the contribution of mode 2, right? That's the contribution of mode 2. Now, let me put it like this. Contribution of mode 2, right? Okay. Now I'm going to erase a little bit over here and say, what if I actually had not just one input, but I had all three inputs? If I had all three inputs, then this would apply, right? How would it look in that case? Then the contribution to the second mode would have been phi, the second one, which is ABC, right? And I would have the same ABC transposed here, right? Times the alpha 2. So the numerator would be, I put this just to guide myself, it would be this times this would be, well actually let me stick to the second one. So this would be A times B times alpha 2, this would be B squared times alpha 2, and this would be CB times alpha 2, right? I would also have these numbers had I measured everything, right? I mean, I'm sorry, had I applied excitations in all three coordinates, then this form would have applied, and I could have been able to write the numerator like that, the denominator being S minus lambda 2 times lambda 2 to the P. This would be the contribution. And let me see. Remember, this is the product. I'm just using it to guide myself, right? So I'll erase it now. So you see that the numerator would have looked like that, right? Had I had all of them, there would be something here. But the point is not that. The point is that that is the second column if I had all of them, right? And if I only have one, I have that second column. Because that second column is ABC times tau 2, in the case where we only had one input. And it thus follows that this column must be the same as that column. Therefore, we conclude that A times tau 2 must be A times B times tau 2. We conclude that B times tau 2 must be the same as B squared times tau 2. And C times tau 2 must be the same as CB times tau 2. And from any one of those three expressions, you either divide by A here, divide by B here, or divide by C here, you get, what did I do? No, I didn't write this down. Didn't write, sorry, my mistake. I don't know where my head is. A times B times alpha 2, B squared times alpha 2, CB times alpha 2. Sorry about that. So A tau 2, B tau 2, C tau 2 must be equal to AB alpha 2, B squared alpha 2, CB alpha 2. Dividing here, you would find that alpha 2 is equal to what? To tau 2 divided by B, right? And if you do this one, you will get that it's tau 2 divided by B, and if you get this one, you'd get that it's tau 2 divided by B. So that means that I was able to calculate the constant without actually having to have loads at the three locations. I only needed to have load at one of the locations where I was measuring, so I could get one column because from there I can find what the constant is. Once I have the constant, then I can come back to here, and suddenly, without having to have the load applied in all three places, I was able to compute a transfer matrix that is now 3 by 3, right? So, the summary of this discussion will now be presented here. So the summary is that the transfer matrix can be written in this form. And therefore, if you have n measurements, your transfer matrix will be m by m. Even though you might only have one input, and that's provided that that one input is collocated with at least, well, not with at least, that one input is placed in a position where there is an output, because that's the only way that we know that one column twice. So if you only have one input, you can still use this because the column, because the value of the constant alpha I is equal to what? It is equal to tau I divided by what? By the value of the mode shape I at location of loading. Okay, so alpha I is simply equal to tau sub I divided by the mode shape at the location of the loading. Of course, we cannot know this unless we have a sensor there, right? But if we have a sensor at the location of the loading, which is necessary, we can calculate the alpha. Having the alpha, we can come here and calculate the transfer matrix of the size of the outputs. Notice the huge importance of this result, because what this means is this. If I have a system like this, right, and I put, let's say, an accelerometer everywhere, which is not difficult to do, right? I could put an accelerometer at all levels. That's not very costly. I only need to have, well, there's some caveats sometimes depending on controllability, but I only need to have, according to this, one input. So if I put the input here, okay, which is collocated with this output, then I will be able to calculate the transfer matrix for this system just as if I had applied inputs everywhere. Because I'm going to get something that is 1, 2, 3, 4, 5, 6, 7, 8 by 8 transfer matrix, right? Instead of 8 by 1 transfer matrix in the original case, right? That's huge, huge importance. Also, it may be that I do not measure everywhere. I only measured, let's say, here, 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 and here. So if I have those measurements, I have 4 outputs, right? The question is, how many inputs do I need? Well, if I have an input on this side over here, I can get my transfer matrix to be a 4 by 4 because my input is at the location of an output. So I can calculate these constants and use the formula in the square here. If, however, I were to apply the input, not at the location where there was a measurement, but for example here, right? Then I do not know what the mode shape is at the location of the input because I don't have a sensor, and I would not be able to use this formula. I'd have to go back to the original formula and in the general one, and in this case all I would be able to find would be a matrix that is 4 by 1. So it is very important when one does testing of this nature for the input to be collocated with one of the outputs. Okay? Now you may have sometimes more than one input, and in this case you get several estimates of the alpha, and one could discuss, okay, you know, how to select the best estimate and so on, but that's a little beyond our available time in this class, so we'll just leave it at this. Now, in the homework, I have given you matrices A, B, C. Okay? So, let me refer to the homework. So, in the homework, I have given you matrices A, B, C in discrete time. Okay? Matrix in discrete time, and the time step is 0.02 seconds. I have asked you to extract the flexibility matrix from these results. Now, the flexibility matrix is the transfer matrix evaluated at s equal to 0. Okay? So you need to do this assessment as s equal to 0. Now, n is the size of A, right? Because that's the order of the system. So what you have to do in the homework, right, in step 1 is what? You have to convert your discrete time matrices to continuous time. So you have to do a discrete to continuous transfer. So now, instead of A discrete, B discrete, and C discrete, you have A continuous, B continuous, and C continuous. And of course, C discrete and C continuous are the same. And the B depends on the assumption on the intersampling of the load. But we should use the zero order hold, which I think it's the only formula that I have given you, other than the fact that B continuous and B discrete. We use sometimes the fact that B discrete was approximately B continuous times delta T, right? But we have a better one, which is called the zero order hold. So you do the discrete to continuous transfers. Now you have your A, B, C. Now once you have your A, B, C, then in your step 2, you're going to have to find what are the mode shapes, right? So you're going to say that you have to solve the eigenvalues and the eigenvectors of the A continuous, right? So you, how should I say this? I will say it like this. A times phi is equal to phi lambda. So I don't give you the steps in MATLAB. You should know by now that with A phi equal to phi lambda, you know, you need to solve for phi and lambda, right? That's the I command. So with A times phi is equal to phi times lambda, you solve for the eigenvalues and the eigenvectors. Once you've solved for the eigenvalues and the eigenvectors of the A, then in step 3, you calculate the vectors phi. So the vectors phi are in the matrix capital Phi here, which is just simply your C times these, right? So you calculate those. Now, once you calculate those, then in step 4, you calculate your tau as the inverse of your phi matrix, right? Which are the eigenvectors of the A, multiplied times your matrix B. At this point, you have every entry that is needed to do this summation. The homework is such that the matrices A, B, and C, if I did not say it there, I think I did, but if I did not say it, we have acceleration measurements. So P is equal to 2. Okay, we have acceleration measurements, so P is equal to 2. Then with P equal to 2, evaluate this. At S equal to 0. Do that summation, and that's your flexibility. Okay? If everything is done correctly, you should find that that flexibility matrix is of course symmetric, and that's it, right? That will conclude the homework. So I think that we have one lecture left, which will be which will be Wednesday tomorrow. And so on the lecture tomorrow, whatever I do, I'll also wrap up the course and make sure that we are all set with everything. But for now, I'll just stop it right here and let you work on it.